is 2.2, and today we will be learning about grinding cycle. So let us see what is grinding cycle. Without going into any explanation, let us look at this video. It is very important that you look at this particular video. So this grinding machine is a very small grinding machine. Safety norms are being not observed. I would never recommend anyone to be near such a grinding machine or using such a grinding machine. See, this is the grinding wheel. Doesn't have a wheel cover. It is extremely dangerous. The grinding wheel is rotating in this direction, and this individual is standing here without any protection, and there is no wheel cover around. However, it is serving my purpose. It is unfortunate that I am using this video, but it is serving my purpose. So what this guy is doing? What happened? He is giving down feed now. Just now, if you have seen, he is giving down feed. So here, yes. Who is it?
Oh, sir, it was okay. Actually, you was not seen, sir. That's why, sir, I'm calling you.
So he has entered?
Okay. Yeah, it is, sir.
Okay, thank you so much. Thank you for your help. So now this guy is giving a down feed. So as he is giving the down feed, the wheel is coming down. There is a rudimentary mechanism to take the wheel down. These are all rudimentary mechanism. This is a built up thing. It's not exactly a professionally made grinding machine, but it will serve my purpose. So after that, what is it doing? He is giving VW, and as you can see, the spark stream intensity is very low, and strangely enough, as you can see, he is not giving any further down feed. Still there is machining going on. What does it mean? It means initially if he has given 20 micron of down feed, in the very fast pass which is going on now, that 20 micron was not removed. That 20 micron was not removed. So here he is giving, this is the first pass he is giving, and that 20 micron was not removed. Without giving any further down feed, if he reciprocates, as you can see, he is doing that, he is getting further removal. So this is the first pass. Second pass, however, gradually the intensity of the spark is reducing. So our observation is something like this. He is giving down feed once. Let us assume that down feed is 20 micron. In the first pass, spark intensity is very high. Second pass, no down feed, but spark is present. However, its intensity is down, and that goes on for third, fourth passes. What is the concluding remark? Concluding remark is that 20 micron down feed did not get removed in the first pass. So there is some problem. You are giving 20 micron, 40 micron, whatever you are giving, that is not getting removed. This is the example of surface grinding. This is occurring in all kinds of grinding. Now, this is the classic grinding wheel, surface grinding situation. This is NS, this is VW, this is A, throughout your course. You will see this diagram n number of times, and this particular grinding wheel is experiencing forces. It is experiencing a force in this direction, and this is experiencing a force in this direction. These forces are applied on the grinding wheel. We have already discussed grinding wheel forces, so these forces will get applied. One more thing, you know, Fn is more than Ft. I do not recall whether I have given this fact earlier or not. Fn by Ft is typically 2 to 2.5 for steel, and it is Fn by Ft is still higher for carbides and ceramics. This I believe I have written earlier. There is one more thing, this being a plunge surface grinding operation, there is no axial force. We do not require axial force to explain grinding cycle. So what was grinding cycle? The essence of grinding cycle is that in the first pass you give 20 micron, it doesn't get removed. Without knowing that if you give another 20 micron, something happens. Without knowing that in third pass if you give another 20 micron, something happens. This gentleman knew that in the first pass if he gives 20 micron, it doesn't get removed. So he gives second, third, fourth passes without adding any further downfeed. Now let us see how we can analyze this. For doing analysis, we have to understand a bit of background. This is the grinding spindle that you do not get to see. This is the back side of the spindle. This is a V pulley. So it would be connected to a motor, and from the motor the speed would be transferred to the pulley. From the pulley it would be transferred to the grinding wheel. This is your grinding wheel. Earlier this was the force Fn and Ft, that was our front view, and this is the side view. Here Fn is acting upward and Ft is towards you, and this is rotating in this particular direction. These are the forces which are being applied on the wheel. I think this is wrong. Ft would be away from you, it would be across. So you are looking from the right hand side. So this is the side view. This is your table. Number 1 is your table. Most of the time on that you have a magnetic chuck. This I did not explain earlier or ever identified. On that magnetic chuck you have workpiece mounted. If your workpiece is non-magnetic, then a vise would be mounted on the magnetic chuck, and on that the workpiece would be mounted. So here my main point is the grinding wheel would be experiencing a force in this particular direction, and there would also be a tangential force. Now this is a schematic representation. So this is your wheel, this is your pulley, this is your shaft, these are the bearing locations. Here also you had those bearing locations, and from the bearing location the grinding wheel is at a distance of L, and this is being acted upon by primarily a force Fn and a tangential force Ft. This Fn force will deflect, this will deflect the wheel. So this would be this black one would be the deflected portion of the spindle. If it deflects by 3 micron, and if you have given a downfeed of 20 micron, you can understand that 20 micron would not get machined. So 20 minus 3 micron, 17 micron would get machined. This is your first pass. In the second pass, you do not know this has happened. So you add another 20 micron. So the machine tries to remove altogether 23 micron, and once again a deflection occurs, possibly a deflection of 4.5 micron, and this game goes on. How we can analyze this game? This particular thing we can analyze using three methods. One is a numerical method, one is a analytical method, another one is a tabular method, just for demonstration. Just for demonstration. This does not capture all the physics. This is for demonstration of grinding cycle. What is grinding cycle? To demonstrate that, this tabular method is excellent, and that's what we are going to do initially. So all are inside, no one is waiting in the lobby, so we can continue. So this is the tabular method. There is too much of data in this particular thing, so do not try to look at the whole slide. I'll explain them one by one. First, concentrate on this table. Only this table, whatever is given here, not any other table. Not this is our table number 1. Do not concentrate on table number 2, 3 or 4. There is something given here. This is a 0th table. You need not have to bother about that as well. This is what? This is pass number. Pass number we will designate by a symbol P. What is this? This is set down feed. How much you have set on the machine. This is designated by AS. This is effective down feed. So this is what is effective down feed. I will talk to you later. This is deflection in micron. How much is the deflection? In the previous slide, we have told you that the deflection is around 3 micron or so. This is the actual down feed. Actual down feed is the effective down feed minus the deflection in micron. Yes, someone is trying to talk. What is it?
Sir, board is not seen, sir.
Screen is not being shown.
Yes, sir.
Okay, please wait. Now is it being shown?
Yes, sir.
Okay.
It is okay.
So fine. So once again, you bother only about table number 1. Do not bother about table 2, table 3, table 4 for the time being, or table 0. I am explaining table 1, simultaneously explain table 0. This is pass number. So pass number is P, set down feed is AS, effective down feed I will come later on. Deflection in micron is this capital D. Actual down feed is this, where is it, A, and effective or total down feed is AT, which is shown here. How much is effective down feed in a pass? Effective down feed in a pass is whatever you have set in that pass plus the deflection in the previous pass. Now in this we are assuming that we are using a old grinding machine, and in each pass whatever is your actual down feed, there is a deflection by 35%. So in the first pass, 0th pass, there is no down feed, total down feed is also 0, there is no deflection, there is no actual down feed. Why? Because you are not grinding. Now in the first pass, you give a down feed of 40. As because in the previous pass, deflection was 0, previous pass was non-existing. So 40 plus 0 becomes 40, this 40. 35% of that is your deflection, so 14 micron. So 26 is the actual deflection. Now go to the second pass. Second pass you have once again given 40. Now 40 plus this 14 becomes 54. This is the total actual downfeed, total effective downfeed. 35% of that is 18.9. This I have done in Excel. Hopefully I haven't done any mistake. And 35.1 gets removed. In this way, if you do calculation, let us stop our calculation till 10th pass. Why do I stop at 10th pass? Because my idea was I would remove 400 micron of material. Why? Because this was my grinding allowance. After machining, this much material was kept to be removed by grinding. How would I remove that? I would remove that 40 micron pass, 10 number of passes. This should solve my problem. Let us see whether it solves my problem or not. After 10th passes, as you can see, there is a total deflection of 21.5 micron. That means 400 minus 21.5, which is 379.5 micron of material has been removed. So the basic purpose of grinding, which is achieving better tolerance, is lost. However, operators know how to take care of that, and that is the reason after 10th pass he provides few more passes. In this particular case, he gives 5 more passes, and let us see what happens. I hope you can see, because still the screen share is on. Now what you can see, there is one more interesting thing. Your requirement was in each pass you should remove 40 micron of material. You should remove 40 micron of material. That unfortunately is not happening. That is not happening. It is not happening at least for first 6 passes. So here the actual downfeed is less than 40 micron. It is less than 40 micron. Where is it happening? It is happening from 7th to 10th pass. Okay. 7th to 10th pass it is happening. 11th pass you have not given any downfeed because total 400 micron has been given. Despite that, actual or effective downfeed becomes 21.5. Where from it comes? It comes from the unmachined part which is remaining there from the previous pass. And then the calculation goes on, and as you can see by 15th pass hardly anything is left out. So you have almost achieved the better tolerance part. This was demonstrated with 35% deflection. So it is an old machine, not a good machine. If you go for 35%, this 6 becomes 8. Steady state grinding, this phase which was 4 pass long becomes 2, and after 5 more passes you have 0.6 micron still left unmachined. So this is situation is even bad. This is more like a representative grinding wheel where the deflection is 15%. As you can see, from 4th to 10th pass you get steady grinding. From 1st to 3rd pass gradually your actual infeed is increasing and approaching 40 micron, and within 3 passes you have nothing left to be machined. So basically 14th and 15th pass are not required. So if you have a good machine, you achieve a lot. What do you achieve? You do not need to give lot many passes after your desired number of passes of 10, whether it is 10, 20, whatever it is, you do not need to give it. So that is the way to go forward. Now what we will do is that we will do a calculation. Take out your calculator and you will help me in doing that. So this is once again same, only thing is that deflection is 10%. So this being 0, this being 40, this is the set one, this is the 0th pass. So 40, this one plus this one would become your actual. Now tell me how much would be D and how much would be A. D is the deflection in first pass, A is the actual material removal or actual down feed. Deflection has to be calculated at 10% rate. It is even a newer machine, even a better machine, it is even better than 15%. So let us do this calculation. How much would be this? NA, please unmute. All of you can unmute and respond one by one. Whenever you are responding, please tell your name. So how much would this deflection be?
4.
4. So how much would this be?
36.
36. Very good. Now in the next pass, this is once again 40, but unfortunately you have some unmachined parts. So 40 plus 4, this becomes 44. 10% of that is the deflection. So this becomes 4.4. This becomes 39.6. Next one is once again 40. Unmachined is 4.4. So this becomes 44.4. This becomes, if we go up to first decimal place, 4.4, and this becomes 40. And then rest of the calculations remain same. So what you achieve is that, as because it is 10%, within the third pass itself, you have achieved steady state. If you continue, let us say this is the 11th pass and this is the 12th pass. Now in 11th pass, as because you have given 40 micron passes at the rate of 10 passes, you are giving 0 because your grinding allowance was 400 micron. So here how much it would be? It would be 0 plus this 4.5. So this would be 4.5, and whatever would be remaining unmachined is 0.44. So this would be around 3.96. Next one would be once again 0. This is 0.44. So hardly everything would get machined. So this would be 0.4 or something. I am not sure about the arithmetics, but this is the idea. So from this idea, we have to understand some of the characteristics. See, in this way, if I give you a numerical problem, you can very well plot how AT, deflection, actual downfeed, everything is going to vary. What is the assumption in this case? Assumption is that you know deflection is a percentage of your effective downfeed, and your effective downfeed in a pass is nothing but your set downfeed in that pass plus deflection in the previous pass. This equation was also written here. So these are the nomenclatures for this tabular thing. Once we go into numerical example or analytical, we will be using a bit different nomenclature. There is a reason for that. We will do that. But this is the way grinding cycle occurs. So what is the takeaway? Initially, there is a phase when whatever is your set down feed, you do not achieve that. Then there is a phase where whatever is the down feed you set, that you achieve. Then unfortunately there are some extra passes required to remove the material completely, and as you can see here, there is nothing left to be removed. This is material deflection in micron, so there is no deflection in this particular plus, so there is nothing left to be removed. So to achieve your desired better tolerance of grinding, instead of 10 passes, you require more number of passes. These are the characteristics of grinding cycle, and let us see what are the consequences. So what are the consequences? Variation in actual downfeed from the set downfeed. So if I plot this is number of passes or pass number, and this is actual downfeed which we have used as A, the variation would be something like this. And this is your set downfeed. After 10 passes or whatever is the required number of passes, what would happen? Gradually, your actual downfeed would vary. So, this is called one particular phase, this is called one particular phase, and this is called another phase. What are these phases called? First one is called spark in phase. Gradually the intensity of the spark increases because your downfeed actual material removal is increasing. Second phase is called steady state grinding, and the third phase is called spark out phase. Here gradually the intensity of the spark goes down. Now because of this variation in actual downfeed, because of the variation in actual downfeed, UG varies, FT varies, FN varies. That I am not going to plot on this. That would come as an assignment at a later date, and you will get to do the assignment and you will see it for yourself. That assignment can be done using MATLAB. I have come across, though I have forgotten, a particular resource available which is very similar to MATLAB, which is free and it can be downloaded and used. If you do not want to use MATLAB, this can also be done in Excel, but you need to know Excel better. So either you can learn MATLAB, which would be an asset for your career, or you can still continue use Excel. And already I have explained what is spark in and spark out. What is the industrial implication of grinding cycle? Industrial implication of grinding cycle is that your grinding allowance in our example was 400 micron. This is too large a grinding allowance. What do you mean by grinding allowance? This is the surface. After machining, you kept 400 micron to be removed so that you get a exact dimension X. Okay, so this is grinding allowance, and you decided that this 400 micron you would remove by 40 micron passes and 10 such passes. What you end up with in this diagram, this is the 11th pass, this is the 12th pass, and this is the 13th pass. You end up with 13 passes. So what happens to your grinding time? Grinding time goes up by 30%. So what happens to your productivity? It goes down. So there is a grinding cycle that we cannot avoid, but unfortunately we have to pay some prices. What are those prices? Because of existence of grinding cycle, the productivity will go down and grinding time will go up. Please try to understand, if it is not a plunge grinding, if it is a traverse grinding, and the size of the surface that you are grinding is say 400 millimeter long and 200 millimeter wide, and you are taking a CS, that is the cross feed or traverse feed of 2 millimeter, and you have to give 3 or 4 more passes just for sparking out, how much time would be lost for grinding? So it would become a very low productivity operation. However, we cannot avoid it because why? Because of this reason. Because my spindle has finite stiffness. Because of my spindle having finite stiffness, I cannot get rid of grinding cycle. It would always exist and I have to live with it. I have to understand it. And one understanding is that quite often operators would not give any down feed and will give 4-5 finishing passes. So what he is trying to do by giving those finishing passes is to achieve the required tolerance without sacrificing other things. Now what we are going into a particular slide which is very crowded. So once again, this video would be with you, so you can always pause this video and later on try to understand, because this you will not be able to understand possibly in a single go, because this is typically done in a blackboard. I cannot do that because writing on a PPT is rather time consuming. So I have prepared this a priori. There is no, though it is a synchronous class, but feedback is less because of our nature of interaction. So I have solved a numerical problem, and this numerical problem I have solved using numerical approach, not a tabular approach. Here we do not have any assumption that 10%, 15%, 20% deflection takes place. Instead of that, how much deflection is taking place is decided by somebody else. So here the whole gamut of data is given. Vs is 50 meter per second, Vw is 100 millimeter per second, that is 6 meter per minute, Bs is 25 millimeter, Bw is 10 millimeter. It is a case of plunge surface grinding, and this is a numerical technique to solve a grinding cycle problem, and you have 40 micron passes, 10 such passes are to be given. What else? Fn is 2.5 times Ft, this is given as an information, and then there is something else given. This is the stiffness of the spindle. This is the stiffness of the spindle, which is 10 Newton per micron. So if there is a normal force of 20 Newton, the spindle will deflect by 2 micron. Now these are the symbols. Symbols are same: P, AS, A, AT. There are two new symbols. Instead of D, delta is being used for deflection, the final deflection of a pass, and small delta is being used deflection within a pass. There is an iteration counter I. Later on we will go for analytical solution where this iteration would not take place. Here first and foremost you have to understand why iterations are required. We will make you understand. I will try my best to do that. So first thing I am going to do is calculate UG. For calculation of UG I need a equation. UG equal to 15 plus 210 a to the power minus 0.8. This is given to you. Where from is it coming? Have I solved any problem? No, you people have solved. Please recall, this 210 was 209.9. So I made it 210. This, where is it? This minus 0.8 was minus 0.778. So I have rounded them off and this is my equation. Only thing is that in this equation UG will come out in joule per millimeter cube and A has to be fit in this particular equation in micron. So I am using UG. So 15 plus 210 to the power 0.8 minus 0.8, and this I have taken as 40. Why have I taken it as 40? Because this is A11. What is A11? A in the fast pass in the fast iteration. How much is it? It is equal to the set value in the fast pass. So A1. If there was any deflection in the previous pass, there is no previous pass, this is the first pass. If there was any deflection within the iteration, this we will not understand for the time being. Let us assume this is also 0. So this becomes 40. That gives me a calculated value of UG equal to 25.99. So UG in my first pass, in my first iteration, why iteration is coming, I will explain later on, is 25.99 joule per millimeter cube. Now I have to get FT. FT is 25.99 into VW into BW into A. A is 0.04. Why? Because of this equation. Divided by 50, that gives me FT value of this one. Fn is 2.5 times FT. So that gives me 51.98. So how much is the deflection in the first pass, first iteration? 5.2. Now I'll try to explain why we require iteration. Please try to understand, this you have taken as 40. However, after doing calculation, you find out this as 5.2. So your A actually was not 40, it was 38.8. For 38.8, you did not calculate UG, you did not calculate FT, you did not calculate Fn, you did not calculate delta. You assumed that it was equal to 40. But when you took it as 40, when you have assumed it to be 40, you found out there is a deflection. And this deflection is 5.2. Is this the deflection in the first pass? No. Why it is not? Because this is not 40. So this is an intermediate calculation. This is not the final value. So with this intermediate calculation, we calculate A12, that is in the first pass, in the second iteration, how much is my A. Then the cycle continues, the wheel rotates, wheel means the wheel, philosophical wheel rotates, the cycle continues. So A1 in the UG in the second pass, first pass, second iteration, this is second iteration counter, becomes 27. FT in the first pass, second iteration, becomes 18.98. Fn becomes 47.46. So deflection becomes, because it is divided by 10 Newton per micron, it becomes 4.8. I am going till first decimal place because I am using calculator. So is this your final deflection? Typically whenever we are doing iteration, we stop and check what was the value of the same variable in the previous one. So this was 4.8, in the previous one it is 5.2. That means if I re-put it here, I would not get the same value. So I calculate A13 once again and I get 35.2. So calculation goes on, and after some time what happens, you will get that this becomes once again 35.2. That takes place in the fourth iteration. In the third iteration it was 35.2 and in the fourth iteration it is 35.2. So we say we stop the iteration process and now we have a final deflection of 4.8. This is called delta P, final deflection in a pth pass. This was shown here, deflection final in a pass, and this is deflection within a pass, that is for different iterations. So delta I is iteration I, or delta Pi is pass number P and ith iteration. So this we do delta P, in this particular case delta 1 becomes 4.8. Now what would be the first value of A in the second pass? Very simple. Forget about any equation. Try to use your logic. This one. This is whatever you have said. It is 40 micron. This is whatever was unmachined, 4.8 micron. Plus there would be minus something, that is what? Minus delta 2, 0. It was also there in the previous slide. Delta 1, 0. What is 1? Pass number. What is 0? 0 is the iteration. This is your first iteration. So delta in the previous within iteration is 0. So in this way we carry on calculating. So here it is also given delta p comma 1 minus I. So in this way if you calculate, you will come here. Now I would not, there are two things. I'll keep this statement. You fill up this form using, you fill up this particular table using calculators, using Excel sheet, anything. In that way you will solve your second pass, and then you will come to the pth pass. In the pth pass, let us assume that this is 8 micron, and 11th pass, this is 11th pass, not pth pass, 11th pass, AS is 0 micron. So A 11 1, that means 11th pass and first iteration would be AS 11 plus delta 10 minus small delta 11 comma 0. This is pass number, this is iteration number. So this one would become 8 micron. Why 8 micron? Sorry, this would become 0 micron. Why 0 micron? Because of this, plus 8 micron because of this, minus 0 micron because this is 0th iteration. So A11 1 would become 8 micron. From that, what would you calculate? You would calculate UG 11 comma 1. Then what would you calculate? You would calculate FT 11 comma 1. Then Fn 11 comma 1. Then delta 11 comma 1. Then you will calculate A 11 comma 2. How would you calculate that? AS 11 plus delta 10 minus delta 11 comma 1. And once you have calculated this, then this cycle continues here. Only thing is that this counter gets incremented by 1. I do not know C. Possibly in C, if you write 1 plus 1 plus plus, that means it gets incremented by 1. I hope my C is good enough. I did not learn C. I am really old. So not like you. You people do not know what is Fortran, and I do not know much about C. So if you agree that iteration loop will continue till such time when delta 11, sorry, when delta 11 I becomes equal to delta 11 I minus 1, then you stop your iteration. And this will continue till 12, 13, 14 pass, till 400 micron material is removed. Now we will try to show you the detailed calculation.